Exercise 11.12 is asking you to think about these radical reactions, radical halogenation reactions, like we were drawing the mechanisms for in the previous video, but to think of them from the perspective of synthesis rather than from the perspective of mechanisms. So hopscotching straight from the beginning to the end, how can you quickly predict the end so as a chef you know what type of dish you're going to make? Now they're using radical bromination, and the truth is that of the different halogens, bromine is the most reliable halogen to use. It will give you the least messy of products. Your products will be, you always get some mixture of products. The radicals are very reactive, and they'll try to stick to any position on a molecule that they can. But in the case of bromine is relatively large, and it sticks onto a relatively reliable place on the molecule. So you end up getting relatively pure products with bromine. And so bromine tends to be the halogen that you do radical reactions with. So in these reactions, they're saying, okay, let's do radical bromination. What product would you get? Just thinking in terms of synthesis. If you treat this with molecular bromine in the presence of light, remember light is symbolized by H nu, where the V-looking thing is really the Greek letter nu, and that stands for the frequency, how often light waves are hitting you. H is just Planck's constant, so it's a conversion factor. If you do that, where will the bromine add? We saw in the previous video that when you do these radical halogenations, you add a bromine onto the hydrocarbon. Where does the bromine add? And it adds wherever you would have the most stable radical. The most stable radical would be an allylic radical, but we don't have any pi bonds here, so you can't have an allylic position. So instead, the most stable radical would be on the most substituted position. Now, it might be tempting to put a radical here. Certainly, that carbon is very substituted. This carbon is bonded to 1, 2, 3, 4 other carbons. But if you remember from the mechanism of in the previous video, the halogens, the radical halogens that you have after the light hits this and you get homolytic cleavage, those radical halogens rip off a hydrogen. They're so reactive that they react with the first thing they bump into. That's the stuff on the outside of a molecule. That's the hydrogens. And so this radical would react with the hydrogens on these carbons before it ever got to this carbon buried deep in there. So you're looking for the most substituted position that has a hydrogen on it. And here, that is this tertiary carbon on the left side of this molecule. There's a hydrogen there. One of these bromine radicals can abstract it. That would give you a radical there. That's the most stable radical you could have on this molecule. That radical will react with the second bromine radical that we made, and ultimately the bromine would add onto that position where you form the most stable radical. So just predicting the products, you put the bromine where you on the most substituted position that has a hydrogen. Okay, so we walked through the rationale there in some detail. Let's see if we can do this a little faster for these other ones. So we're doing radical bromination. We're treating this with molecular bromine in the presence of light, H nu. And what you're looking for is the most substituted position. Now really you would look for the allylic position if you have it, but we don't have any pi bonds here, so you're looking for the most substituted position that has a hydrogen. And that's this carbon here. That carbon is tertiary. The carbon is bonded to 1, 2, 3 other carbons, so it's tertiary. And so that's where the most stable radical could form, right? This creates two bromine radicals. One of the bromine radicals rips the hydrogen off here, abstracts that hydrogen. You get the most stable radical on that tertiary carbon, and the second bromine radical sticks to that and adds onto that position. And notice in these last two steps, notice the transformation that you make. You take an alkane, a molecule that has almost no reactivity, and you put a leaving group on it. You open up the world of substitution and elimination. And with elimination, you make a pi bond, and so open up the world of addition too. So these radical reactions are a way of turning alkanes into anything you want to, basically, through substitution, elimination, and addition. Okay, for C. So what would happen if you did radical bromination with this, if you treated this with molecular bromine in the presence of light, H nu? Well, we're looking for the most substituted position that has a hydrogen on it. We have a lot of very substituted carbons. This is quaternary, quaternary, and quaternary. All those carbons are bonded to 4 other things, but they don't have any hydrogens on them for one of these bromine radicals to rip off. A bromine radical bouncing around would react with the hydrogens outside of those before they ever got to those buried carbons. The most substituted carbon that has a hydrogen is this one here. There's a hydrogen there, and that's facing the outside of the molecule. You would create a bromine radical with the ultraviolet light. You'd create 2 of them. One of them would rip that hydrogen off. It would give you the most stable radical you could have without a pi bond. That's the tertiary radical. And that would react with the second bromine radical that we made in a coupling step, a termination step. So that the final product would have a bromine on that position, on the most substituted carbon that has a hydrogen on it in the original molecule. And just watch out for the allylic position if you have a pi bond. So that is exercise 11-12, where you're just looking at this from the perspective of synthesis. You're turning alkanes into halo alkanes, alkanes with halogens on them. Really powerful reaction. Now, exercise 11-14 is really doing the same thing. The only difference is here, and you can see this with these special bonds, those 3-dimensional bonds. Here, they're giving you chiral centers. Now remember that these radicals exist in p orbitals. And if they exist in p orbitals, then the atom that they're on only has 2 p orbitals left. Remember that carbon atom has 1 s orbital and 3 p orbitals. If it's using one of the p orbitals to hold the radical, then there are only 2 left to mix with the s. So it's sp2 hybridized. sp2 hybridized atoms are trigonal planar. So radicals are flat, they're planar. Radicals are trigonal planar, just like carbocations. And so when they react with a bromine radical, they are going to give you a racemic mixture if you create a chiral center. Because the radical is flat, some other radicals will attack from the top and create one enantiomer. Other radicals will attack from the bottom and create the other enantiomer. Because the radical is flat, there's no preference for how a radical could couple with it. So here they're saying you're doing radical bromination again, predict the products, and include the stereochemical outcome. Draw whichever enantiomers you get. So if we treat this with molecular bromine and ultraviolet light, H nu, Planck's constant times the frequency, the bromine will add to the most substituted position that has a hydrogen on it. And that's this carbon here. That carbon is tertiary. 1, 2, 3 carbons. It's the only carbon in the molecule, excuse me, that's tertiary. And so the hydrogen here, you'll form your 2 bromine radicals. One of the bromine radicals will rip that hydrogen off, create a tertiary radical there. The second bromine radical will couple with that, and you'll have your bromine add there. Now there are no chiral centers in this molecule. If you notice, going around the ring in one direction is the same as going around it in the other. You run into the same things at the same points. CH2, 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 CH2. That's the same either way you go around the ring. And so this is not bonded to 4 different things. It's not a chiral center. You don't have to draw any enantiomers. If you take the next molecule, you do a radical bromination with that. You treat it with molecular bromine in the presence of light, usually ultraviolet light, represented by Planck's constant times the frequency, nu. Then you look for the most substituted position on the molecule that has a hydrogen on it, and that's this one right here. There's a hydrogen going away there. So when you shine the ultraviolet light on the bromine, you get homolytic cleavage, you get 2 bromine radicals. One of those bromines rips this hydrogen off. The other electron in the bond to the hydrogen becomes a radical. Now we have a tertiary radical. Notice that it forms here and not here. This top one is quaternary, 1, 2, 3, 4. But there are no hydrogens there. And so that atom is too buried for the radical to reach it. The radical would react with the hydrogens on other atoms before it ever reached that quaternary carbon. So the radicals rip hydrogens off the molecule. So the most stable radical is here. It's a tertiary radical, and it's flat. So when you have the radical, you would actually, to draw it technically more correctly, I would take this and draw that as a normal bond that's in the plane. Those radicals are trigonal planar. So when the second bromine radical attacks that, sometimes it will attack from the top and so it would be coming out at us. And by attacking at the top, it will push this methyl group away from us. On the other hand, because this radical is flat, sometimes the bromine radical will attack from the back, in which case it'll be going away from us. But if it attacks from the back, it'll push this methyl group toward us, and so that would be represented by a solid wedge. So you'd get a racemic 50-50 mixture of those 2 enantiomers if you did a radical reaction, or radical bromination of that original alkane. Okay, let's try C. So what would happen if we treated this with molecular bromine in the presence of light, represented by H, Planck's constant, times nu, the frequency of the light? This creates 2 radicals. One of those radicals rips off a hydrogen here, and the hydrogen would be the one that's attached to the chiral center, because it's the most substituted position on the molecule that has a hydrogen. It's true, this carbon to the right of it is more substituted, but there's no hydrogen there for the radical to rip off. So the hydrogen gets ripped off by the first bromine radical. You form a radical on this tertiary carbon. Radicals are flat. They're trigonal planar, sp2 hybridized. And so to represent that flatness, I would have just a regular line to represent the bond for that methyl group at this point in the reaction. The second bromine radical then couples with this. Now, it can attack from the top, in which case the bromine would be coming out at us, and that would push the methyl group so that it's going away from us. It would be represented by a dashed wedge. But because the original molecule is trigonal planar and flat, there's no reason why the bromine would just attack from this side. It could just as easily, just as often, attack from the back, in which case it would be going away from us, and that would push this methyl group towards us. So it would be represented by a solid wedge. So if you did this radical bromination with this original molecule, you would end up with a racemic 50-50 mixture of those two products. Okay, one more. What if you did a radical bromination with this alkane? If you treated it with molecular bromine in the presence of light, represented by H, Planck's constant, times nu, the Greek letter nu, which represents the frequency, how frequently the waves are hitting you of the light. So, where would the bromine add? Well, this creates a bromine radical. The bromine radical would rip a hydrogen off the molecule. Where is there a hydrogen on the most substituted carbon? That's on this carbon right here. It's the hydrogen going away. There. There are two other more substituted carbons. This carbon in this tert-butyl group is tertiary, is quaternary. It's bonded to 1, 2, 3, 4 other carbons. And this carbon here is bonded to 4 other carbons, 1, 2, 3, 4, but they don't have hydrogens on them, and so the radicals wouldn't react with those carbons. They would rip a hydrogen off other carbons before they ever got to those buried quaternary carbons. So this hydrogen, though, is on the outside of the molecule. It's available, and when you rip it off, you get a relatively stable radical. So one of the bromine radicals that you make with the homolytic cleavage using ultraviolet light rips this hydrogen off, and you end up forming a radical here. Now, radicals are trigonal planar. They're sp2 hybridized. They're flat. So I would redraw that methyl group just as a regular line to represent that this is a flat molecule, trigonal planar molecule. Okay, now our second bromine radical can attack this, but because it's flat, it could attack it from either side. And it would do so with equal probability. On the one hand, it could attack from the top, in which case it would be coming out at us. So that second bromine radical would be bonded with a solid wedge. That would push this methyl group in the opposite direction. That would be going away. On the other hand, the radical was trigonal planar. It was flat, so there's no reason why the bromine would only attack from that side. It could just as easily, just as often attack from the other side and be going away from us. If it attacked from the back, that would push this methyl group toward us, and that methyl group would now be represented by a solid wedge. And so, if you did a radical bromination with this original alkane, you would end up with a racemic 50-50 mixture of those two enantiomers. So in this video, we've done a couple exercises where we considered these radical brominations from the perspective of synthesis, just drawing the product, the haloalkane, that you get when you do the radical bromination. We pointed out how powerful that is because this molecule has no nucleophiles or electrophiles on it. This molecule has an electrophilic center and a leaving group. It can do substitution and elimination. Once you do elimination, you create a pi bond and you can do addition. So this radical reaction is very powerful because it opens up the other three reaction types to you by putting a leaving group on the molecule. The one other thing we saw is that the radicals that you form are trigonal planar, they're sp2 hybridized, and so they're flat. And so if they form at a chiral center, you will get a racemic mixture of the two enantiomers because the second radical could react with equal probability on either side of the flat carbon radical. And so hopefully this video helped you a little bit with thinking of these radical halogenation reactions from the perspective of synthesis.